All right, everyone, thank you for coming to the annual Carlin and William Reeburgh Endowed Earth System Science Lecture. I'm Andre Drake. I'm a new assistant professor in Earth System Science here at UC Irvine, and I'm a physical oceanographer, so it's particularly my pleasure to introduce our distinguished speaker today, Dr. Susan Lozier. Susan Lozier is the Dean of the Colleges of Sciences and Betsy, Middleton, and John Clark Sutherland Chair and Professor in Earth and Atmospheric Science at Georgia Tech. Very long title for a long and distinguished career. Susan has many awards, including being a fellow of both the American Meteorological Society and the American Geophysical Union, which she recently served as president for. And also is a recipient of the Henry Stommel Research Medal, which, if you're not familiar, is what I would say one of the top, if not the top, award in our field. And Susan's research is quite generally focused on the role of ocean in climate variability and change. And Susan will tell you a bit about some of the advances that she and her team have done on this topic. So take it away, Susan.
Thank you, Andre. Everybody can hear me fine? All right, thank you. I want to thank Andre for the invitation, and thank you to all who I've met so far during my visit here. I've enjoyed your hospitality. Appreciate it. So, I have been interested in the overturning circulation for a long time, and there's a lot of things that I'll tell you about why I really love the overturning circulation. But one of the things I really like about it is its origin story. The overturning circulation actually was described by a sentence in 1800 by Count Mumford. And I'm going to talk to you today about all the measurements we're taking to understand the dynamics, the variability of overturning circulation. But something that's always fascinating to me is that there was a single profile of temperature that was taken, and from that, Count Mumford was able to deduce about the overturning circulation. So, quick story. Back in 1751, anybody know this? Anybody know this story? Yes, so happy about this. Okay, back in 1751, there was Reverend Stephen Hales in England who was very curious about deep ocean temperatures. At that time, people thought the deep ocean was still, life, and dark, obviously dark. Very little was known about it. So he asked Captain Henry Ellis, of a British slave trader, to take measurements on the transit across the tropical Atlantic. And Captain Ellis agreed to do that. So he and his crew stopped in what was called the torrid zone, and with a wooden bucket where the bottom was taken out as well, and they fitted valves to the top and bottom of the bucket, such that when it was lowered over the side, the valves would be open. And then when they started pulling it up, the valves, would be shut from water pressure. When they got it onto the ship's deck, they would stick a simple thermometer of Mr. Fahrenheit's made by Mr. Bird into the bucket, and they would record the temperature. And then they just repeated that. They would lower the rope down further. So in 1751, as far as we know, that was the first recorded temperature profile of the ocean. And what they found in this letter that Reverend Hales, that Captain Ellis wrote back to Reverend Hales, what he said is that the temperature decreased proportional to depth, so temperatures were getting colder the further they went down, until they reached a depth of about, they used the fathoms then, but it turns out that it's about 1,200 feet. And at that depth, the temperatures would not decrease anymore. They weren't getting any colder. But he recorded at the time an interesting fact. He said that the temperatures that they recorded at depth were about 53 degrees Fahrenheit. And he found that curious because he didn't, it was like 30 degrees colder than the temperatures at the surface. So he just noted that curiosity. He sent the bottom of the letter to Reverend Hales. He said, "We hope this satisfies your scientific curiosity. We don't know what it means, but we are pleased to have found the source of cold water to cool our baths and wines in this most disagreeable weather." So they were very happy for the cold water, didn't know what it meant scientifically. Henry Ellis sent that letter on to the Royal Society in London, and it sort of just sat in the archives until Count Mumford, most everybody knows Count Mumford studied convection, and he stumbled upon it in 1800, and he was very puzzled by the fact that those deep temperatures were so cold. And he surmised they were even colder, given the methods. Obviously, we were bringing that bucket back up that bucket was not waterproof, and so he surmised that the deep waters were even colder than the recorded 53 degrees Fahrenheit. And so he surmised, by thinking about, he understood that the tropical air temperatures were really not that cold in the evenings or not that cold in the summer. And so he wrote a simple sentence. He said, "It seems to me incontrovertible that the cold at depth in the tropics could be, for any other reason, could result from any other reason than cold currents from the poles." And he said, and if that's the case, there must be a warm current that's returning to poles from the tropics. And so with that single profile of temperature, then he surmised what came to be known as the global ocean conveyor belt, which was popularized that term was popularized by Reeburgh back in the 1980s. Today, we don't really talk about the conveyor belt, we talk about the meridional overturning circulation, in large part because we can mathematically describe what the overturning circulation is like. That was in 1800. And then starting in the 1920s, 1930s, oceanographers were crisscrossing the basin. And what these cross-sections, hydrographic cross-sections were able to do then was to create a spatial context for the overturning circulation. So Rumford said, here we see cold waters at depth in the tropics. They must have originated at high latitude. And so once oceanographers started making these cross sections, we could see them. And now it's turning on its times. There we go. So what we're able to see are really the signatures. Here's the signature of the deep water from high latitudes in the North Atlantic. This is the salty water that's penetrating the deeper Atlantic and moving down, spreading rearward. So these cross sections gave us the first spatial context for this overturning circulation. And then the temporal context was really supplied by this tritium concentration in the North Atlantic. So in the 1950s and 1960s, tritium was a byproduct of nuclear bomb testing that was done both by the Soviets and the US during those decades. And so tritium was not at measurable quantities at all in the ocean until that bomb testing. And so what we was able to see vividly in this, again, cross-section as part of this geoscience program, which was intended to give a baseline of ocean chemistry, we can see vividly the uptake of tritium by this overturning circulation. So what Rumford described back in 1800 and was picked up on by Wally Broker was really the understanding of very high latitudes during the winter. The surface waters are cooled and the surface waters become cold and dense, and they're denser than the waters underneath, and so they sink and then they start spreading to distant parts of the globe. There's much more to the story. They upwell through a series of mixing and return to the North Atlantic. So I am primarily talking today about the North Atlantic, or the Atlantic overturning circulation, where the deep waters form at high latitudes in the North Atlantic, not the Southern Ocean overturning circulation. So here in the North Atlantic then, in the early 70s, was a very strong realization of the conveyor belt, this overturning circulation in action. So you can see this penetration. And then in the 1990s, we started understanding the deep ocean as a reservoir for anthropogenic carbon dioxide. So this is sort of unimaginable. The Rumford understood in that, and when he wrote, he understood that this overturning circulation would have a big impact on the redistribution of heat across our planet. But here, what we see from these results, from a series of cruises that were done from the North Atlantic across the Southern Ocean and back up to the Aleutians, if we look across that transect, what became very obvious is that the penetration of anthropogenic carbon dioxide was throughout the ocean, but it was particularly occurring in the deep North Atlantic. And in the deep North Atlantic, where it's about 80 and 90% of the altitude waters are formed. And so what we saw from tritium, the penetration of tritium at depth, here in the 1990s, we started seeing then the penetration of deep nitrogen carbon dioxide. Now, as many of you in this room know, that uptake of carbon at the surface depends vitally on oceanology, ocean carbon, also ocean physics. But its export to depth and then the subsequent transport of that, the equatorward spread, depends vitally on the ocean physics, and in particular, depends very strongly on overturning variability. So understanding then that the carbon uptake depends on the overturning variability, the question was, well, to what extent can we expect changes in the overturning variability? As we're interested not only in how that variability might impact the heat distribution or redistribution, but we're also really interested in how that variability might impact that nitrogen carbon uptake. So at the turn of the century, and this is the turn of the century from the 20th to the 21st, our understanding of the overturning variability at that time was really based on the assumption that variability was really on long time scales, on millennial time scales, on time scales of ice ages. So in my world, in the world of physical oceanographers, we weren't paying that much attention to the variable overturning circulation, sort of time scales that were longer than we were interested in at that point. We also considered the overturning variability meridionally coherent, so that picture of the conveyor belt is sort of a conceptual model we have. If you measured one place, the variability at one place, you would see it at the other place. Oceanographers were busy trying to understand the source of the water masses that were in the overturning circulation. The Labrador and Nordic seas were considered the source of those deep waters. And there was a very strong expectation that that overturning circulation was primarily, the conduit for that was the eastwestern Atlantic current. So deep water masses were formed in the high Atlantic, and the high Atlantic, they moved along the deep western Atlantic current and spread to distant parts of the world from there. So around this time in the turn of the century, things started changing in terms of our expectations about the time scale of the overturning circulation. So this was a very famous in my world, collection of studies. This was put out by the National Research Council about climate change in 2002. And in that, it was promoting some recent studies that have looked at simultaneous changes in ice sheets, both in Antarctica and Greenland, and show very synchronous changes in the global air temperatures. And the authors concluded that the climate record over this past 100,000 years, it clearly indicated that the climate system had undergone shifts on timescales of decades or even years. And the mechanism, the cause for that was attributed to the overturning circulation. So this got everybody's attention. That the overturning circulation could possibly change on timescales this small. And right about that same time, there was a study put out by Gary Bryden and colleagues. It was in 2005. They talked about the slowing of the Atlantic meridional overturning circulation at 25 north. And the reported reduction in AMO over 5 decades was reported to be 30%. This was based on repeat hydrographic sections, these 5. And what you can see here, they were looking at the transport per unit depth, total depth down to 1,000, down to 6,000, and based on those 5 measurements over 5 decades, they reported a decline of 30%. So that the work done by paleoceanographers to say, actually, things could change very quickly and followed abruptly with this study saying that it had slowed 30% over 5 years, got a lot of attention. And so there was a big effort, both in the modeling world and observational world on both sides of the Atlantic, to understand overturning circulation. So I do want to note then that these measurements, the overturning circulation is not measured directly. So it's using hydrographic measurements to infer the geostrophic velocities, and from there to get the overturning circulation. So Right after that study then, there was the first direct observation of overturning circulation was put in place, and the reasons I just told you about, this program was referred to and still is referred to as rapid, as in rapid climate change. So this is put in at 26 degrees north. It's an effort by UK and the United States, and it has moorings, there's all sorts of instrumentation to get the first direct measures of the overturning circulation. So put in 2004. Now, what I want, I'm using that NRC study and using that rapid array and saying that rapid array first went in 2004, so we're 20 years down the road. And so I want to structure my remarks today by basically saying, after 2 decades down this road of an intensive effort, I'm trying to understand the AMOD, the meridional overturning circulation. What are we doing? So this is a brief summary to start with what I'm going to be talking about. Don't need to be biting our nails about an AMOD's collapse, but we should be worried. Overturning circulation is very noisy. I'll talk about that. Their belt paradigm has not been particularly helpful with our efforts to understanding overturning circulation. Salinity matters might be obvious, and deep water formation is optimistic. I'm going to go through each of those. So first, this may be something all of you know, but a lot of people, the main thing in the popular press, what everybody wants to know is the AMOD going to collapse? I feel like I read something about it every 2 weeks, maybe every 3 weeks. So I just want to put up here, I still am a big believer in the IPCC report. The good news is we don't expect a collapse, in this century. So we do know that if we did have one, it would cause abrupt changes, but it is likely that it not will. We just have that expectation as the climate continues to warm. It's very likely. We see that all models forecast that. And in these models, that these changes are attributed to the reduction in deep water mass formation. So we're going to be talking a lot about that. The one thing I'll point out here before we move, and this will be relevant to something I'm going to show later, is that all of these show that by 2020 we should already be experiencing. It's pretty clear from all the models. The other thing I'll point out is there's still a lot of spread in these models, and this is where people like me who are focused on making observations feel as though this is an important role to ground truth the models. Okay, so where are we with the rapid array? I just downloaded this data the other day. This is the most recent rapid time series, again, 26 degrees north. So this is almost a 20-year record. So lots of lines here. The one I'll bring your attention to is the red line. The blue, the green, and the pink are, if you sum those, you get the total overturning, which is here. There are people that will tell you that this is a declining signal. There are people that will tell you that it's not a declining signal. In fact, I was just at a workshop in Oxford at the end of March, and this was about 40 people who were intensely focused on AMOD observations, and we all tried to come up with one statement we could all agree on that stated of the AMOD. And the sentence, I don't have it exactly right, but it was something like, there's no observable decrease in the AMOD anywhere, either because the signal to noise ratio is too small, or it hasn't changed. So you'll read different things about it, but I think that's the consensus. Now, shortly after this array was put in place in 2004, a very interesting study came out by Gilman et al. And this had a big impact on me at the time. So what this is showing is this is an ocean-only model, and they're showing the mean overturning circulation here as a function of latitude. Again, this is a model with depth. But the important thing here was that this was the first time that they were looking at the Mach anomalies. So again, latitude as a function of time. And what this study pointed out was that there was a break in the meridional coherence of these Mach anomalies at approximately the gyre-gyre boundary, the subtropical subpolar gyre in the North Atlantic. And so that whole idea about the conveyor belt, you measure one place, that's the variability, you get it somewhere else. This was starting, to break down in the study led to that. Also at the same time, we started understanding that what was being measured at rapid, a good part of that signature was wind driven. So back in the day, people talk about the overturning circulation or the conveyor belt, they talk about the Lozier circulation. But on the time scales that we started being interested in this, it was very clear that wind-driven variability was also playing a role. And there were studies done that were decomposing that rapid signature and showing how much the local winds were driving that. So there were those of us in the bushel community that were very interested in understanding what the overturning circulation was doing at the high latitudes. And why the high latitudes? The high latitudes, we wanted to go where the deep water masses were formed. So down there at 26 degrees north, there are no deep water masses being formed. It was chosen for different reasons, having to do with the meridional heat flux. But after we understood that the role of wind forcing at 26 degrees north, after we also understood that there wasn't any meridional coherence, or we suspected there wasn't, I led an effort, and still leading an effort, in this international program to measure the overturning in the subpolar North Atlantic ocean, where these deep water masses are formed. So this was deployed in the summer of 2014. Here's a quick tutorial for those of you who don't live in this neighborhood. I'm going to be talking about the Lozier Sea, the Reeburgh Sea, the Iceland Basin. I'm interested in the waters formed in these three subpolar basins. Also interested in the waters coming over this Greenland-Scotland ridge from the Nordic seas, Denmark Strait overflow water, and Iceland-Scotland overflow water. So I'll be talking about those. So here, this OSNA, there are six countries involved in this. It's a big operation. The OSNAP array stretches from Labrador coast to one side of Greenland, southwest Pacific Greenland, and from the southeast of Greenland all the way over the Scottish Shelf. And so this array has been in place since 2014. And the goal is to measure the overturning circulation, the meridional heat transport, and the meridional freshwater transport as well. This is a quick look at the mean salinity to orient you as well. So here's the Labrador, Reeburgh, Iceland basin. And so what we see here are the waters of the upper limb of that overturning circulation. These are warm and salty waters that are moving northward toward the Nordic seas. And the waters that are carried in the lower limb are these water masses, homogenized, cold, and fresh waters. These are the waters now moving south. So this is what a cross-section of this OSNAP array looks like. This is our OSNAP time series to date. And I will say that when we were up there, we thought we're not going to get a signal as noisy as they are down in the subtropics, where all of that wind variability is playing such a strong role. And we have a signal that's just as noisy up in the subpolar North Atlantic. But the one thing that really surprised us was the difference and the distinction between OSNAP West, which is the Lozier Sea, the overturning in OSNAP West, and then the overturning in OSNAP East, and that's the eastern part of the basin, which includes the Reeburgh and Iceland basins. And why that was surprising is because so much of the focus had talked about the Lozier Basin as a driver of the overturning circulation of those waters. That's where they thought the majority of the waters were formed in addition to the Nordic seas, and there just been a heavy observational emphasis placed on that basin. So first thing we wanted to understand is why is the Lozier Sea not contributing, and what we understood from a study not too long ago is that when we measure the overturning, we're always measuring it in density space. And that overturning comes about because waters become denser. So in density space, I've talked to you you earlier about the cool winds that are going over the North Atlantic, the density can also change because of salinity. And so we have both temperature and salinity that can impact the density of the waters. In addition to thinking about the overturning density space, you can also just measure the overturning in temperature space or the overturning in salinity space as well. And what we found when we went to the Labrador Sea, when we went to Host West, we found that we had large overturning in temperature space, large overturning in salinity space. So these are transports as a function of salinity and as a function of potential temperature, such that the cooling of the water mass was being offset by the freshening of the water mass. So that even though these were large contributions here, 12, 14, 11 spiridrops, the overturning density space was more like 3 spiridrops. So it was much reduced. So we just had 2 years of observations at that time, but if you look in a model, this is an ocean reanalysis model, OC5, and we look over many more years, you can see the same impact. If we look at the contributions of density, contributions of salinity to density, the contributions of temperature to density, and then density itself, what we see is that the strong compensation of the salinity and temperature are really reducing the contributions to density. So why does this matter in terms of what we're trying to figure out about deep water formation in the North Atlantic? As we move ahead, we're expecting not only there to be warming, but we're also expecting there to be a lot of freshwater input. And where we have a lot of freshwater input is particularly in the Labrador Sea. The Labrador Sea is rimmed with shelf and slope waters that are really exposed to ice melt, both coming through the Davis Strait and also from Greenland and then ice off of Labrador as well. So a study that a postdoc worked on with me, Yana Biva, she looked at an idealized 3-layer model. This is the Labrador Basin, and she was looking at the boundary current that is rimming this basin, coming along Greenland and along Canada. And she was looking at the change in the density as that water moves along that boundary. So here's the distance along that boundary. And what we know is that the freshwater forcing the surface precipitation evaporation and very little impact, that what really matters is the exposure to all the runoff. And so based on that model, she was able to explain that even though while we have this cooling going on, which is creating the densification, the freshening that's created by the mixing with all these waters is offsetting that, such that there's very little density condensation. That helped explain why we were seeing so little dense water mass formation in the Labrador Sea. Some, but not that much. Now, when we go in to the other part, the eastern part, which is called OSNAP East, and we look at over our OSNAP record, we see that OSNAP West, we see that the density, the production of waters in density space is depressed relative to the production in salinity and temperature, but that's not the case in OSNAP East. The production of the waters in density space is actually robust. In the eastern part of the basin, salinity plays a much smaller role because of the temperature of the waters than it does in the western part of the basin. So this says over at OSNAP East, at least to date, it's really thermally driven. These deep water masses are thermally driven. So what interests us really is, as we think ahead, it's like, well, where are these deep waters in the eastern subpolar basin exposed to fresh water? And if you remember the map that I showed you earlier, these waters, I'll go back to that quickly. These waters in the subpolar basin are really only exposed to this fresh water here off the Greenland coast compared to the waters that are rimming the Labrador Basin. So when we go back and we look then at the dense water formation in the Erminger Sea and apply that same model, what we see that as a function of path length, we don't really have the density compensation. That the salinity here in blue, those colors are washed out, but this is the salinity contribution to density, play a very little role. That in fact, the temperature is really driving all of that deep rock formation. This helps us think ahead then that in large part, that's we're talking about the decades ahead. Is it possible that enough fresh water might make a difference? So what we're seeing here is the model in gold, the model's initial TS. This is the final, so you see a real density change here, and you see how well it observes the initial conditions. So overall with these studies, what we're trying to understand is what is the sensitivity of the deep water formation differentially to temperature and salinity changes in the decades ahead, and also differentially geographically. So where are the water mass formation areas that are going to be most impacted by the freshwater amount? Now, the surface water transformation, some of you in this room know this, but others don't. It depends on the surface density, right? It depends on temperature and salinity. And also then depends on the buoyancy force. Depends on that jet stream that's moving over the Sutherland Atlantic that's resulting in that strong loss of buoyancy, that strong loss of heat. So 30 years ago, when I was a graduate student at the University of Washington, we had to memorize sort of here's where seawater was formed, and we had to know its temperature and salinity, and then we knew what the ice had, ISOW, DSOW, temperature and salinity were. So we had in our mind that it was very fixed where these water masses were formed, just really deeply connected basins. But our view now of the water masses, if we look at what the transformation is, so this is the surface force water mass transformation, and we're looking, I'm going to go through these maps, and these are at different densities. So this is the density. This is the density here. These are the lightest densities. This is the density of the lightest water that's formed. And what I want you to see is that as we go through this, the water mass formation is really throughout the Sutherland Atlantic. It's not in one particular basin or the other. We have this very strong meandering jet stream moving over these very cold, dense waters. It's a very variable, spatially variable density field as well. And so we can, for any different winter, have water mass formation in very different parts of this. And so what this means is that in thinking about where most of the dense water is formed, it may really just come down to geometry. And that I'm showing by this very simple graph here. So we're looking at the annual transformation, so that means over the course of 1 year, how much deep water is formed over the whole east region and over the whole west region. So again, the Lozier Sea goes down west, and then ice and basins, ice coast east. So earlier I showed you that one of our big results was that there was a huge difference between how much water was formed. Turns out it's about an order of magnitude that's very, a factor of 3. That's actually very similar to just the difference in the surface area. And in fact, if we do a simple scaling here, relative to the surface area, we think that these transformations are about the same. Now, this isn't the whole story, but I always say it's not nothing either. So rather than thinking that we can have water mass formation just in this basin because the conditions are just right, that's what I said earlier, that this is more opportunistic, that we have a variable density field, variable buoyancy field, and we are producing this water mass in different areas. What happens to those water masses? So whether we're talking about oxygen, temperature, salinity, or nitrogen, carbon dioxide, we're very interested in how the pathways, spreading pathways to equator, interested in the rates, how fast does that water get there. Now, for decades, until the 1990s, our understanding of the abyssal circulation was really guided in large part by Stammel's theory of the abyssal circulation here, and the idea was that this is based on potential vorticity dynamics. And even though nobody really had ever seen any polar interior flows, the idea still held that the water masses that were introduced to the deep ocean moved down western boundary currents. So oceanographers went to the western boundary currents to measure the tracers, the CFCs, temperature, salinity, oxygen, everything. A large focus was on the deep western boundary current. And for good reason, there's strong currents there, and they do a great job transporting things. But starting in the 1990s, there were a number of studies that started giving many of us an idea that the deep western boundary current was not the only avenue for deep waters to reach the equator latitudes. So Amy Bauer and I, a colleague of mine from Woods Hole Oceanographic Institution, we looked at what are called the upper North Atlantic deep waters. So in the lower limit of the overturning circulation, upper waters, lighter, denser waters. The densest are those waters from coming over the Greenland-Scotland Ridge, the overflow waters. So we put waters purposely in the deep western boundary current, in upper North Atlantic deep water. These are Lagrangian floats that are trapped acoustically, and we let them go for 2 years, and this is what we do. So clearly we don't see a strong signature of a conduit for the deep western boundary current. In fact, more floats stayed within the subpolar ocean than went into the subtropics, and those that went into the subtropics did so via interior routes. Here is just our observations when we get these trajectories for 2 years. And so we did a modeling study, and here was our expectation just of the models. So this is waters in the trajectories in the model that are released 50 years, and we see this is the distribution of what we would expect at the exit of the liners. So not the western boundary current light, fills the interior, things recirculate. This is model-based only, like we've had no observations of Lagrangian trajectories in the ocean back here 10 years ago, so this was model-based. So when OSNAP was started back in 2014, in addition to putting in a mooring waterways, 6 different waterways across the subpolar North Atlantic, Amy Bauer and I teamed up again to put in a float program. So again, what we're trying to understand is where is this deep water going? And here this float program wants to focus on the overflow waters, so the densest waters that we find in high latitudes of the North Atlantic. And this again is a very famous spaghetti diagram that's here on the left. I'm going to just take a moment to walk you through this. So we have arrays here, which are float deployment sites here and here. So here are the waters coming down, Iceland, Scotland overflow waters. Here are the Denmark Strait overflow waters coming down. And here also are where we thought we would also capture Iceland, Scotland overflow waters. So I mentioned to you early on that back in the day, physical oceanographers weren't that interested in the overturning circulation because they thought timescales were too long. One place where the paleo-oceanographers world and the modern oceanographers world connect is in pathways. So when paleo-oceanographers are going out, taking cores and trying to understand the pathways of these deep waters, it's very important for them to understand that they are actually in the pathway of these overflows. So on the right here is just to convince you that we knew what we were doing, that these are where all the float deployments were, and they were all below these dashed lines which indicate the density of water masses that we were interested in tracing. And so when we wanted, just like in the previous studies, since these float trajectories can only be out there for 2 years, we're just limited by battery power. It's tremendously expensive. We have about 80 Raycos floods. The sound sources themselves about $200,000. So it's very expensive programs, so we always have with a modeling study. And so what I'm showing you here, here's our observations over 2 years. We're using all of the flow data to create this probability distribution map using our hot chain, comparing it to one model, another model, and we're looking at the East Greenland, the West Greenland Ridge launch, and the East Greenland Ridge launch. So what I'm just hoping to convince you that the main features after 2 years were picked up by these models. These models did not show that much difference. But what I'm going to use the next one to do is to show you what was quite interesting to us. So previously, when physical astronomers had talked about the fate of these water masses, we talked about them in terms of their density. You know, because we're always so preoccupied that the water's viscosity class, you move here, the water's viscosity class move there. So these water masses here, what's called northeastern deep water, is really just a mixture of ISOW and other water masses, but these have the same density. We tagged them at different places. This was tagged on the east side of the Great Barrier Ridge. This was tagged on the east side of Greenland. So very different distribution. This is a very much denser water mass, the Denmark Strait overflow water. And you can see that these have nearly identical distributions. And really it has to do with their initial location. So the water mass, the ISOW that is coming down, a lot of it spreads on this side. In fact, very little of it. It's heavily mixed and sort of loses its identity if any of it gets into the western boundary current. So those two water masses, both in the North Sea, both coming over the sills, are really impacted by the dynamics of the circulation at depth. I won't get into this, but in large part, these waters are blocked by the deep flowing North Atlantic current in this area. So OSNAP, these deep floats, were able to track some of these differences in these water masses. The last thing that I'll go over here then is, for decades, the first study started in the 1980s, people continued to track the property anomalies down in the coastal atmosphere. So people will look in the upper sea and say, oh, it is there's fresh anomalies this year, salty anomalies this year. So they'll look at a record down at Abercombe or at Cape Hatteras and then see what the effective time scale is for those systems. So if we think about, we want to know what happens to that oxygen, the carbon, the temperature slightly as these waters are spreading wayward, we're asking, is the deep western boundary current still a conduit? Even though it isn't carrying all of it, we still count on it to understand what the property signatures are. So very simple study done by research associated working with England Sophie. Here is a schematic deep western boundary current. She's following the 3,000 meter isobath. It's tracking the deep western boundary current from Labrador Sea to Abercombe. And then we're picking a light neutral density for the upper waters, deeper one that's in the lower North Atlantic deep waters, so getting in the overflow waters. And we're just looking at distance, 0 being the Labrador Sea, and then 5,000 kilometers later being here at Abercombe. And we're just seeing if we can track those salinity lines. I think most everybody here could say, most certainly not. This is the R squared in color. That is the correlation between the salinity time series at the exit and then at any point along this path. And here's the lag. So if we have coherent propagation of anomalies, we should see something that looks like this. The lag should increase downstream, and we should have correlation, a lagged correlation with the salinity time series here. So we see there's a very real difference, and what creates that difference? What creates that difference is really the local variance. So again, if we look in the upper North Atlantic deep water at this neutral density surface, we see hot spots that are created really by a meandering deep Gulf Stream, North Atlantic current. If we go down deeper, the lower North Atlantic deep water, we see, which is pretty obvious, a much more quiescent ocean. So really it's a competition in between the convected compared to the local variability. So for the upper North Atlantic deep water, we look at the R squared. We start with a very strong correlation with what's happening in the Labrador Sea. It drops quickly to where we have very low correlations, and that's because we have strong variance along the way. This is essentially mixing the signature. Very different in the lower North Atlantic deep water. We have the variance you can see is much reduced. These are different scales, a factor of 5. So we're able to propagate those signatures downstream. So this also explains when he was very interested in understanding what do we see at the very high latitudes in the subpolar North Atlantic and how can we relate that to what's happening downstream. We haven't been able to find a correlation between what's happening in ocean and what's happening downstream. This gets to the fact that the ocean is very noisy, and these interannual, maybe even little time scales. It's very difficult for us to find any of that meridional coherence. This just shows what I talked about in a way she depicted that I happen to like. When you go down deep enough, you see the R squared here is in color, the size has to do with the local cylinder variance. You see that you just send those signals down where you get a very different picture, very large local variance, and there's no coherent pattern. Last slide here then is to just show this on not just two density surfaces, but you see we can't get any signatures through. We start getting the signal through. With these neutral density surfaces, then it breaks up again, but this is really due to the quality of the polar depth. So all of this is where we're sort of trying to understand where can we get these signatures communicated, how can we, when we're trying to interpret our signatures downstream, at what density surfaces can we set to try to correlate with what's happening at the surface. So 20 years down the road, to be honest, sometimes I think, what have we learned in 20 years? Because there's still a lot to learn. One of the things we've learned that is really, there's just such strong variability. I mentioned that when we moved to the subpolar North Atlantic, we thought, well, we're so smart, we're going to move up there where the dominant signal, is just going to be that much cleaner. It's a very noisy signal, even in those latitudes where we know that deep water formation plays a large role. Why we're so interested in this deep water formation where is because I talked about the climate models. If you look at the climate models and where these deep waters are formed, they're kind of all over the place. And so we're just really trying to understand not only where they're formed, but why they're formed, and how they might be affected differentially by warming and or freshening as we move forward. Been working with some climate modelers, and getting the density compensation right in models is very difficult because it relies on getting that mixing correct with those fresh waters that are governing those basins. Talked about the deep western boundary current. And I also talked about this last point. When I say there's no consensus, there are papers out there that say, based on temperature record or based on this, it is slowed. There was a very nice paper by Chris Hypooch earlier, and he talks about the 4% decline in the Gulf Stream. He also says this could also be radicular variability. So there are lots of different signatures. None that I would say have been convincing enough for there to be a general consensus on that the economic is slowing. So we keep measuring. But the best thing we have for projections are the climate models. And one thing I feel very gratified about is that there are a lot of modelers that are now using the study as well as the lack of data to get ground truth and understand to try to improve their models. So I'm gonna stop there and see if you have any questions.
If people want to raise their hands for questions, and I'll pass the mic over.
It's a long throw.
So Susan, if you go back to Jim Hansen's, he was 99th century, it's in Climate Model 88.
Yeah.
Okay. Now, do you think there's going to be, is there a magic bullet here, or you just have to wait another 20 years? Or is there some new measurement that you can come up with beyond the snaps and the warnings? Is there some way to actually do a better job of diagnosing what's really happening?
Yeah, I mean, that absolutely is what people are asking. Is there something, I'll say, people have tried different proxies for the AMOC, and I would say there have been no reliable proxies to date for the AMOC. We're trying to focus on how we can do this more efficiently, but I don't know that we can get around measuring the ocean's circulation. I don't know that we can measure just the ocean property field and faithfully reproduce the AMOC. And once you get into measuring the ocean circulation field, it's intensive, yeah. And it's the deep ocean field too, particularly if you have the boundary lines. So, does anybody here have a very efficient, quick, easy way to measure the ocean circulation?
Yeah, I have a follow-up question.
Okay. You have a way to measure it efficiently and quickly? Good.
Yeah, well, thanks. So Laura Chimoli and Jake Getty have this paper where, going back to your idea from the very beginning of the talk of using tracers like tritium to infer the circulation, they argue that the changes in chlorofluorocarbons in the Southern Ocean are suggestive of a slowdown in the Southern Ocean circulation. And so presumably you could apply similar ideas to the North Atlantic to infer a slowdown.
On what time scale?
A few decades.
Few decades, yeah, potentially.
Yeah, I don't know, it won't be as quantitative as this, but at least it would give you the sign of the circulation change. Other questions?
Thank you, Susan. It's a really good talk. I am intrigued by this, like freshening, compensating with this warming, so essentially you don't have any density changes. I wonder if the same thing might also happen in the Nordic Sea, so you would have a change, like less change of the demonstrated overflow in the next couple of decades. And also, do you think, the similar like shelf water melting contributing to this dense water also happens in the Southern Ocean, like near Antarctica? So do you expect a similar situation happening?
Yes, so I think the density compensation, so basically where you have the waters cold enough, which would be in the Southern Ocean, which would be in the Nordic seas, such that in the equation state that salinity is playing an important contribution or having an important impact on the density, that's where it's possible. Interesting, I heard a great talk on, you were probably in the same section, maybe you didn't have to remember who it was, that they were looking at the climate model and saying that, well, if we have a slowdown in the overturning for the subpolar North Atlantic waters, if maybe the Nordic seas picks up, have you heard this? Because of the ice melt and there's more open ocean that's subject to deep convection. So it was, do you remember that? Were you sleeping during this? I'm kidding, we were not. But that was really an interesting idea, not focused on density compensation so much, but really focused on the Nordic seas and what might happen to the deep waters there. But I do think as those waters melt, that density compensation is, yeah, absolutely vital.
So my question has to do with both of the lower latitudes and your new array in the north. There's a lot of it looks like coherent interannual variability, and like for the global temperatures, we know that there's a big effect like El Nino, different oscillatory patterns. And if I was curious, to what degree do you predict the interannual variability in these arrays? And if you remove it, does that help you with identifying if there's a long-term trend? Is it like sort of analog to removing an ENSO signal from a temperature record to look at the longer-term trend?
Yeah, and maybe we will be able to, so the host map right now, I showed you that 8-year time series. And so, NAO has a time period of 5 to 7 years, or 3 to 5, depending on what we do. So our time series is not yet long enough that we can start removing those modes of variability. So maybe we remove the seasonal variability, not the big deal, but yay, after 6 years. So, yes, but the rapid time series is now 20 years. A lot of that variability is due to local winds. And actually remarkable, they're able to, use pretty idealized model, force it with local winds and capture 70 or 80% of the variability. So maybe in time, with the long time series, we might be able to do that, but not now.
Any other questions?
I have one for now, which is, I think when a non-expert looks at these kinds of mooring arrays like OSNAP and RAPID, they would be surprised that you could get an accurate estimate by just measuring the ocean at just a few points and then integrate over thousands of kilometers. So can you go into a little bit overview of the methods of how you can convince yourselves that this is a robust estimate with relatively small measurement error?
Yeah, happy to do that. I mentioned earlier that I'm happy that these observations feed into models, but the models actually fed into our observational design. So if you've heard what OSSIs are, which are the observing system simulation experiments, you got it, right? So almost all, at least in my world of physical oceanography, before we put something like this in the water, we have simulated an observing system in a number of models. And so in the models, I'm always so jealous because they have data in every grid point and all points in time. But you have the model of truth, right? So you have the record of the overturning circulation, the heat transport, the freshwater transport, and then you subsample. So we pretend that there is just a mooring here, and we take measurements just, monthly, we take measurements just at the depths of that. And then we look at how much can we recreate the mean and can we recreate the variability. So we still use observing system designs. We are trying to come up with an efficient design. So that is one way we do it. So we also are heavily instrumenting the boundary currents. So in the subpolar North Atlantic, the boundary currents are very swift and intense. But in the interior, we are using dynamic height moorings, so we're still using our geostrophic velocities, we're using cargo data, vegetation salinity that go into that. We're using satellite altimeter, so it's all sorts of different instruments that we're doing to capture this integrated measure. So, is that?
That's right.
Okay, at least worth an A- enough.
Okay. Other questions, especially maybe encouraging students or people outside of ESS? Yeah.
Just learning. Sorry, can I ask another question? Is SNAP going on? Like, what's the plan for the future of those SNAPs?
Yes. So we have 2 more years of funding. So we will recover the instruments this summer, and they will be in the water, we know for sure, until 2026. And I was just talking to how difficult it is. So yes, thank you, Adam, for the continuation of funding. So we're working on it. Yeah, it's, this has been funded by NSF. 1 5-year proposal, maybe we can 3 or 4 proposals, I don't remember. But we're really at the point where this gets back, to Michael's question, how do you measure this? There are papers out there that say, yeah, it's about ready to tip. Have you seen those papers? Yeah, tip within the next decade. We are trying to figure out some mechanism where there can be some long-term funding. But I will say it's not cheap. And it's also, there are 5 countries involved in this, so the US has the biggest footprint. Probably carrying 2/3 of the financial cost of this. But the UK is heavily invested, the Netherlands, Germany, and also Canada. So we hope to continue it, but I think everybody here knows about the vagaries of funding. We'd love to hand it off and say, to Noah, here, good luck. But we don't. That didn't sound very optimistic. We're going to continue to fund this.
I have one final question about
Yes.
the potential tipping of the AMOC and potential collapse. So you showed nicely that the IPCC models show that there's a pretty small decline at the 30%, I think,
Well,
by 2100.
yeah.
So there are groups out there and many papers in the press recently arguing that the models are biased. In particular, the model sensitivity to freshwater coursing is biased, and so that they're not as sensitive to freshwater coursing and don't collapse as easily as they should. What's your take on that?
I don't know.
Great, so more research.
Okay, the problem is, I always think like meteorologists, how fortunate they are, right? Because their predictions can fail every single day, right? How many of us have observed a collapse of the overturning circulation? How many of us have predicted a collapse based on some mechanism and observed it or not observed it? So I don't know. I mean, I think it's really difficult. But I will just say it's very controversial about the sensitivity of these models to the tipping point. What is your opinion on it?
Seriously? I don't know.
Oh, yeah. Anybody here know? Anybody want to take bets on the overturning tipping? Do not put money on it.
There'll probably be at least 10 papers every year.
Yes, there will be. And the journalists will be calling me and saying, I mean, actually, that's good. I mean, the papers are out there, the ideas are out there, and we don't want that to be. I sometimes feel like people are rooting for the overturning circulation to collapse. I'm like, I'm not rooting for the overturning circulation. I'm happy with it just chugging along as it is. So, yeah, I'm going to stop because I'm not actually having this conversation.
Great, let's say Susan Lozier one more time.